All right, for part 2 of chapter 9, we are going to continue looking at SN2 reactions and see some factors that can affect these substitution reactions overall. So let's hop into it. First one we already saw when discussing some of the kinetic factors that led to the discovery of the SN2 mechanism. Yep. So let's address that a little bit further, right? Why are methyl halides the fastest and tertiary alkyl halides the slowest? Yep. Well, it all has to do with steric hindrance. Okay? As you increase the number of alkyl groups around that electrophilic carbon, right? Higher number of alkyl groups means you have more steric hindrance. Okay? That decreases the rate of an SN2 reaction because you've got less access to carbon. Okay? So much so that these tertiary alkyl halides don't react via SN2 reactions. Okay? Steric hindrance is a steric effect that decreases reactivity, like we see here. Right? In order for the SN2 reaction to occur, this hydroxide nucleophile has to come in and attack that carbon. So the more alkyl groups you have, right, the more things that are blocking access. Okay? So as you go from methyl, primary, secondary to tertiary, more alkyl groups means more steric hindrance, which means a slower rate. And we can see that in the reaction coordinate diagrams here. Right? Looking at a methyl halide on the left, right, versus a secondary alkyl halide over here. Right? As you have fewer substituents, you see there's a smaller activation energy, so it's faster. The more alkyl substituents you have, the more crowding going on, transition state's higher in energy, the higher energy barrier to overcome, so it's a slower reaction. Okay? And both the number of the substituents is important, but so is the size of the substituents. Okay? Looking at primary, secondary, tertiary is one thing, but also the size of the alkyl substituents themselves. Right? Because take this alkyl halide, for example. Right? It's a primary alkyl halide because bromine here is attached to carbon that's just attached to one other carbon. So yes, it is primary, but it's also reacting very slowly because that next carbon has a bunch of alkyl substituents on it. And keep in mind, backside attack, right? It's blocking approach of a nucleophile. So just something else to pay attention to, right? Look at the total environment of that electrophilic carbon. If there are things that are present there to block the approach of the nucleophile, it's going to react slower. Okay. And we know that we have inversion of configuration from video 1. Okay. Well, why is that? Continuing further, right? It's all about backside attack. Nucleophile comes in, hits that carbon, right? Looking at our transition state in the middle, bond forming, bond breaking, everything that was previously attached to carbon other than the leaving group is now in the same plane. Right? And then we restore sp3 hybridization in our tetrahedral geometry. So you see that it's inverted its configuration. You can think about it like an umbrella popping in and out here. Inversion of configuration for an SN2 reaction. If you're R, you get S. If you were S, you would go to R. Okay? Inversion of configuration, you may also see that referred to as a Walden inversion. What else do we have? Okay? Well, the identity of the leaving group itself can affect the rate of a reaction. Okay? And this is a key idea from all of chapter 9. We're going to continue to see this. Weak bases are better leaving groups. If you're taking notes, I'd jot that down. Weak bases are better leaving groups. Okay? Because weak bases are stable bases, meaning that they can readily bear electrons. Okay? Because when your leaving group, take iodine in this case, right, it had a pair of electrons in the bond to the alkyl halide. When it gets kicked off as the leaving group, it picks up that lone pair that was previously forming the bond. Okay? The electrons that were forming this bond here become a lone pair on iodide. And weak bases are stable. They can readily bear those electrons. And remember from Gen Chem, right, weak bases have the strongest conjugate acids. So we see that right here, right? pKa values of the conjugate acid, HX. So HI, HBr, HCl, HF in this case. Okay. So we've seen earlier in organic, right? HI, hydroiodic acid, is the strongest of the group 17 acids, HI, HBr, HCl, HF. So if HI is the strongest acid, that means iodide is the weakest conjugate base. Remember, strong acid, weak conjugate base, meaning that of the 4 halides, iodide is the best leaving group. And the better the leaving group, the faster your relative rate of reaction. So iodide is faster than bromide, is faster than chloride. Okay, fluoride's not really a good leaving group at all. Okay. So as we see, relative reactivities, right? An alkyl iodide is faster than an alkyl bromide, which is faster than an alkyl chloride. And as I just mentioned, we won't see alkyl fluorides used in SN2 reactions. Okay. Weaker base, better leaving group, faster reaction. How about nucleophiles? Okay. Let's take a look at those. Okay. Table 9.1 in your textbook lists a bunch of common nucleophiles and bases. Okay, we're thinking about nucleophiles for substitution reactions, bases for elimination reactions later on. Okay. Nucleophiles and bases share the fact that they have at least one lone pair. Okay. If something's acting as a base, it shares its lone pair with a proton. If something's acting as a nucleophile, it shares its lone pair with something else other than a proton, typically carbon in organic chemistry. So you see how those two concepts are pretty closely tied, basicity and nucleophilicity. Okay. You measure the strength of a base by equilibrium. You measure the strength of a nucleophile by how readily it will attack an electrophile, something that's electron deficient. Okay. Now we know from the first video that the nucleophile in an SN2 reaction attacks an sp3 hybridized carbon in the rate determining step, the RDS. Okay. So because it's involved in the rate determining step, that means that the better the nucleophile, the stronger the nucleophile, the faster overall rate of an SN2 reaction. So how do we determine that? Okay. Well, a stronger base is typically a better nucleophile. You see those on the left. Okay. And how do I quickly determine that, right, without measuring pKa's of conjugate acids? Something that is negatively charged is a stronger base and a better nucleophile than something else that's neutral. Okay, so drop a proton off of everything on the right, you get these negatively charged species on the left. These are stronger bases and better nucleophiles. Okay, so while everything on this screen could act as a nucleophile, these things over here that are negatively charged are better nucleophiles. Okay. We call nucleophiles good or poor, right? So you see better and poor. We call bases strong or weak. Okay. Now, what about if everything's in the same row, looking at the periodic table? If they're in the same row, that means that they are, give or take, the same size. Okay. So going right, off basicity, whatever the strongest base is the best nucleophile. Okay. So typically going further to the left in this case. But the question becomes, what about size differences? Okay. Because size plays a pretty big factor. Now, what if they're not the same size? Okay. Because the larger the atom, we just said that, right, larger atoms are weaker bases. We see it with iodide compared to bromide and chloride, for example. So larger atoms are weaker bases, which would typically mean that they are weaker nucleophiles. Right? However, the larger the atom, the more polarizable it is, which means that it can move freely towards a positive charge. Okay? More polarizability means more orbital overlap, okay? More bonding, a more stable transition state. up here, right? See how significantly that bond is forming? So now the question becomes, does that greater polarizability help larger atoms be better nucleophiles, even though they're less basic overall? And the answer to that question is one of the trickier parts of chapter 9. It's the fact that it depends on the solvent. Okay, so this slide is restating the question. Does the greater polarizability that helps larger atoms be better nucleophiles make up for the decreased basicity that causes them to be poorer nucleophiles? And the answer is it depends on the solvent specifically. Okay. And we've got two new important terms here, aprotic polar and protic polar. Okay. Polar is not new. You've heard polar before. You know how to identify if something's polar or non-polar. Okay. But within polar solvents, we need to think about if they're protic or if they're aprotic. As a polar protic solvent down here has a hydrogen bonded to oxygen or nitrogen. Okay. So like water or ammonia, those are protic polar solvents. Hydrogen bonded to oxygen or nitrogen. Aprotic polar solvents, okay, are polar solvents that don't have hydrogen bonded to oxygen or nitrogen. Okay? So something like dimethyl sulfoxide, if you look up that structure, that's a aprotic polar solvent. And identifying the solvent present is important because that will control the nucleophilicity. Okay, so answering our questions, no, right? Polarizability does not outweigh the decreased basicity if you're in an aprotic polar solvent. So iodide would be a bad nucleophile, a poor nucleophile. Right? But if you're in a polar protic solvent, then now larger atoms are better nucleophiles, which is summarized in this slide right here. Okay, slide 33. So looking at our halides specifically, as we go down group 17, we're increasing in size, right? But they're getting to be worse and worse bases. They're weak bases down here at the bottom, which is why basicity goes up the other way. Okay. So if you're aprotic polar, the smaller things are the best bases. But if you're in a polar protic solvent, like water or ammonia, the larger ones are the best nucleophiles. Okay. So think about some solvents here. Right? Non-polar solvents, which we're not talking about right now, are something like hexanes or benzene. Okay. But those don't work as solvents for your SN2 reactions because they can't dissolve things that are negatively charged. So you can't have your good nucleophiles dissolved in there. And so they're kind of out of the question. You have to use a polar solvent. Okay. So a polar protic solvent has hydrogen attached to oxygen, listed here, or nitrogen. So water, common one. Alcohols like ethanol or methanol are also common as well. Okay. Aprotic polar don't have hydrogen attached to oxygen. So I mentioned DMSO before. THF would be another one, tetrahydrofuran, dimethylformamide. If you look up any of those structures, you'll see no hydrogens attached to oxygen, but they're still polar solvents. Okay. So why the difference? Right, jumping back to slide 33, why do we see that difference in nucleophilicity depending just on the solvent? Okay. Well, it has to do with what happens in solution. Okay. Because if I take a polar protic solvent here, right, and I put fluoride in it, right, that has really strong ion dipole interactions. Okay. Really electronegative here. Delta positive here. I think about it almost like a hydrogen bond. It's called an ion dipole because this is an ion here. But that has a really strong interaction with a polar protic solvent, okay, which weakens the strength of this fluoride, okay, because it gets surrounded by all of that polar protic solvent. Okay. Iodide, however, has pretty weak ion dipole interactions. So it can still act as a nucleophile and kind of shrug off the solvent that it's surrounded by, okay, which is why the protic versus aprotic is significant. If it's polar protic, those interactions are so strong it weakens those nucleophiles. So bigger is better in that case. right? And iodide would be the best nucleophile in polar protic. However, if it's aprotic polar, right, then you don't have that interaction to worry about. So the stronger the base, the better the nucleophile. And looking at these aprotic polar solvents, right, they have delta negatives and delta positives, but they're not as large as they are with alcohols or water, right? It's just a polar difference, not like a hydrogen bond. So they don't shield those nucleophiles as much, right? Think about this like a shield surrounding the nucleophile. Versus here, it's not going to happen as much. That partial positive is stuck on the inside of a molecule, so it's not interacting as strongly. Okay. And that's why you see the difference. Okay. They can still dissolve things, but they don't shield them. So in an aprotic polar solvent, the stronger the base, the better the nucleophile. Now, your fastest reaction rate, of course, would have no interaction with the solvent as well. So the fastest possible SN2 reaction would be in a nonpolar solvent. It just can't dissolve the nucleophiles necessary, so it can't happen. Or running it in the gas phase as well would speed it up. Okay. One more thing that can affect nucleophilicity, right? Sterics again, but now not looking at just the alkyl halide, looking at the nucleophile itself. Okay, sterics are important there as well. Okay. So let's think about ethoxide in tert butoxide. Now, tert butoxide is actually a stronger base. So the quick assumption would be that it's a better nucleophile. But you see right here, it's a stronger base, but it's a poorer nucleophile. And it's all about the size, right? The extra alkyl groups over here, even though it's a stronger base, make it harder for this nucleophile to go in and attack the electrophilic carbon, right? They kind of block the approach. It doesn't matter when it's acting as a base because it's just picking up a proton here on the end. But when this thing's actually trying to go in and attack a carbon, it's totally different. Okay. So tert butoxide, stronger base, but sterically hindered, so a poorer nucleophile. Ethoxide in this case, right, smaller, it's a better nucleophile. So lots of different factors that affect SN2 reactions. You should know all of them from this video and know the mechanism for an SN2 reaction from the first video. And you see that there's a lot of uses of these SN2 reactions. You can start with something as simple as an alkyl halide. They're readily commercially available. And you've got a ton of different nucleophiles that can react with alkyl halides. You can turn them into an alcohol, an ether, a thiol, a thioether, or primary ammonium, just depending on changing the nucleophile. Okay. But think about the basicity to determine the direction of a reaction, right? These reactions are all going forward, right? Because a weak base can't, right? Look at the difference here, looking at your nucleophile, which can also be considered a base, right? And then the nucleophile or base that's produced. We learned this way back in chapter 2, right? Predicting reactions. These are all irreversible, going from reactants to products left to right, because these weak bases that are produced, which is good, right? It's a weak base is a good leaving group, so that helps us, but it means we also can't turn the reaction around. Bromide isn't going to come in here and attack carbon and kick off that amine, right? So these reactions are always just going in one direction. If you look at that bottom reaction on slide 39 here, that was our reaction from chapter 7, okay, using the acetylate ion as a nucleophile. So that's a lot of information from this video and the first one. That wraps up everything from SN2 reactions, right? In part 3 from chapter 9, we're going to look at the other substitution reaction, which is an SN1 reaction.